All right, so as a reminder from last class, we finished our game. So you make your moves. It's counting the number of moves we have. We use the singleton to do that. Remind me, what's a singleton? It's one of those design patterns. What specific design pattern is that guy? Okay. So you're kind of talking about how we implemented it, but just in general, a singleton, the design pattern for a singleton says it's a good idea to store things that need to be shared among multiple classes in one place. So as you pointed out, you have one class you create, and then that becomes a little storage bucket that screen 1 can grab, screen 2 can grab, things like that. Okay. So in our game, we recognized when you had a winning, when you won, we took you to the winning screen. We counted the number of moves you made, so on and so forth. So we finished up Towers of Hanoi last time. And I want to say I don't think I pushed the final version. So let's go ahead and just commit those changes. I did push it. Sure, for a design pattern. So a singleton, I probably even have it written down here. It's a good idea to put information that needs to be shared between more than 2 activities in one place. And this is kind of the specific answer for Android. You would replace activities with objects if you wanted to be more generic. So if we wanted to create a singleton between us, we would maybe throw something in this drawer up here, and we would all share that drawer for a place that we were keeping a set of keys or something like that. Okay. So up to this point, we've been talking about linear linked data structures. All right, these are the animals we've been dealing with so far. So these are linked lists, these are stacks, these are queues. So all these guys are in a line. Really, linked lists is the generic. Stacks and queues are special purpose linked lists. So actually, stacks and queues are easier than a linked list. Because a linked list, when you write that, it has to be kind of, well, it might be very general purpose because you might use it for a whole bunch of different things. Where a stack, you're always adding to the front, you're always removing from the front. So it's pretty easy to implement. A queue, you're always adding to the end and you're always removing from the front. Also pretty easy to implement. Because where linked lists start getting a little hairy is when you want to start adding or removing stuff somewhere in the middle. Where you have to kind of like perform surgery, like you got to disconnect this, you got this new guy you want here, you got to connect it, and get all the pieces put back together so that now you have a functional list. But in any case, these guys are all linear. It's all in a line. Okay? Even though they're not right next to each other in memory, because that's one of the advantages of these linked data structures that we've talked about. So if we kind of review here. Oh, well, sort of. That's kind of where I'm going with this. So arrays are linear, but not linked. So we don't have a node that links to another node that links to another node. So what does that ultimately mean? That arrays are fast because they are linear and in contiguous memory, which is memory in a row, memory right next to each other. So we can mathematically calculate each individual bucket of an array where that guy lives. Okay, so arrays are really fast. But in the very next sentence here, we could say arrays are memory inefficient because they must request enough memory for the maximum number of elements, let's say. So arrays are memory inefficient because they must request must request enough memory for the maximum number of elements they could possibly hold when they are created. So if I think I might need to hold 1,000 things, when I first create an array, I'm going to say I'm going to block off this chunk of memory here that's big enough to hold 1,000 things. I might only put 3 things in there. So it's kind of like you go out and you get this giant storage container and you put 1 pair of shoes in it. Kind of a waste of space, right? But you have extra space if you need it. But if you need to build the problem is if you go out and you get a little shoebox that can hold 1 pair of shoes, and you need to hold a second pair of shoes, you need to find a bigger box, right? So you need to destroy that. Well, you probably wouldn't destroy the shoebox, but in computer speak, we would destroy that shoebox and we would create a new shoebox that's exactly twice the size, and put 2 pairs of shoes in there. Then when we need 3 pairs of shoes, we would destroy our 2-pair shoebox and create a 3-pair shoebox. Very memory inefficient, right? So we might say, well, you know what? I might need to store 20 pairs of shoes. So you'll create a box for holding 20 pairs of shoes. But you might only have 3 pairs of shoes in there with room to grow. But you're still memory inefficient because you have a whole bunch of memory that you've reserved, but you're not using. Okay? Where our linked data structures, like linked lists, stacks, and queues, they could arbitrarily grow. If there's 3 elements in a linked list and we want to add a 4th, we can just expand its size by 1. And how do we do that? We create 1 new node and then link it to the list. Because they're not sitting right next to each other. They are not in contiguous memory. The memory addresses of those individual nodes might be all throughout memory, but we have a pointer to each one that takes us on that trip through memory. That make sense? So arrays are fast because they're in contiguous memory. We can say that linked lists are slow because they are not in contiguous memory. So we must traverse the list from the beginning to get to a particular, oh, that was butchered, particular element. We can't just go to bucket 3 of the linked list. We can go to bucket 3 of an array because we can calculate the exact memory location of bucket 3 because we know they all live right next to each other. With a linked list, we have to start at bucket 0, then go to his neighbor to go to bucket 1, then go to his neighbor to go to bucket 2, then go to his neighbor to go to bucket 3. And we're someplace else in memory, but in order to get to bucket 3, we had to traverse the whole list. So it's relatively slow. But we'll say that linked lists are memory efficient because they only use as much memory as they currently need to store their contents. Make sense? So this kind of becomes an interesting thing with modern computing. If we go back many years when memory was a big deal, we would have said that linked lists were pretty important, right? If you, because in the earlier days of computing, you might need to store 500 records. Let's say you were a doctor's office and you just opened your doors. Well, the hope is that in a year you're going to have 500 patients. Well, maybe day 1 you don't. Day 1 you have 3. Well, you probably also don't have a whole lot of money. So the amount of memory it would take in your computer to hold a larger number of patients might have been very expensive. And this really used to be a problem. So most of you are, in fact, all of you you've grown up during a time period where memory's always been inexpensive, right? I think I probably told it last when you had in 535, but I always told a story that in 1996, I had a computer with 8 megabytes of memory in it. Have you heard this story before? You've heard this one? So I had a computer with 8 megabytes of memory, not gigabytes, 8 megabytes of memory. And I added a second 8 megabytes of memory to that. You know how much that chip cost for 8 megabytes of memory? It was $1,000. And that was after memory had already dropped in price quite a bit. So if you do the math today, just to kind of give you an idea. If you go out to Amazon, let's give ourselves real numbers. And let's look at a 4 gigabyte, 4 gigabyte DDR4. You just first one that popped up, $50? We'll say it's $50 for a 4 gigabyte chip. Okay, so this is 4 gigabytes. I got an 8 megabyte one. So 4 gigabytes is 4,096 megabytes. So that's 512 times bigger than what I paid $1,000 for. Okay? So in 1996, this chip would have cost $512,000, $500,000 for this chip. Okay, and that's in 1996 money. Then you got to deal with inflation, so it's probably about almost $1 million at the end of the day. All right, so today, if we take that, so we decided that 4,096 megabytes, that's 4 gigabytes. Why is 4 gigabytes 4,096 megabytes? How did that math work? It's 1,024. 1024. Okay, so 1 gigabyte is equal to 1,024 megabytes. 1 megabyte is equal to 1,024 kilobytes. 1 kilobyte is equal to 1,024 bytes. Make sense? So that's how it scales. So 4 times 1,024 is 4096. So if we're doing, I'll just leave that math there. So 4096 divided by, well actually, sorry, not divided by, it's 50 divided by 4096 is about a penny per megabyte. Just round it, a little over a penny, 0.012 cents per megabyte. So today, RAM is about 1 cent per megabyte. In 1996, it was 1,000 divided by 8. RAM was about $125 per megabyte. A little bit different. And this was after memory had already dropped in price quite a bit. This is when it was on sale. It was worse before that. So go back to the earlier 90s, the 80s, late 70s. I mean, late 70s is what it would have been in the extremes. I mean, first of all, we didn't have the amount of memory we had today because it was the cost of producing it was, you would have been better off just buying diamonds. Honestly, you would have been better off buying diamonds. Diamonds would have been way less expensive than memory. But the point I'm driving home here is years ago, memory was a big deal, right? We had to, as computer scientists, we had to be really, really careful about memory because running out of memory and needing to get more memory might not be a possibility. You either A, had too much memory in your computer that you couldn't add anymore, or B, not enough money in your bank account to buy more. I remember I worked at this computer repair shop, and this guy had ordered a custom computer with 128 megabytes of RAM in it, which is not a lot compared to today's computers, right? But back then, that was like obscene. So 128 megabytes of RAM in that computer was probably equivalent to somebody getting, I mean, maybe something like 128 gigabytes of RAM in a computer today. Or at least 64 gigabytes of RAM in a computer today. But more than that, it was probably 128. Like some amount that just people don't get. Because some gamers will order a machine and put 64 gigs of RAM in it just because they can. Because RAM isn't really expensive anymore. I mean, that's not you get a motherboard that can take that many chips, and you just throw a bunch of, you put 8 gigabyte chips in there. So that should be under $100 probably. So if we do 8 gigabyte DDR4, guessing it's probably like $80. So 97, 90, $100. Yeah, so about twice. So an 8 gigabyte chip, yeah, here's $92, whatever. So $800, and you have 64 gigs of RAM, which we're not going to use today, right? It's a ridiculous amount of memory. But punchline is back then, memory was very, very expensive. Even in the 90s, I mean, 1996, we don't think of as being all that long ago. That's not like ancient history, right? 1996 is kind of like a, spitting distance, Let's see, most of you were probably around in 96, maybe barely around. What year were we born? You were 2. Yeah, so most of you were kind of little then, right? Yeah, I wasn't. I was old. It was not little. But then again, I've never really been little. So, but that's not like super, super ancient history long ago. That's in the, some of the software we use today may have been written back then. So some of the decisions that had to be made back then had to really consider memory, where today we don't really consider it that much. Now, things also scale, right? The size of the files that we commonly work with today are a lot bigger, aren't they? There was a time when, like, for instance, if there's like an MP3 that's on the web and you go to download it, and let's say it's 3 megabytes, you don't even think about that, right? You click the link and you expect that it's going to be downloaded within a couple of seconds. Well, in 1996, the kinds of modems we had were like, maybe a 9600 baud modem or a 4800 baud modem. That's bits per second. So even if we go, 9600 bits per second divided by 8, that's 1200 bytes per second, divided by 1024. I'm sorry, that's bytes per second. No, that's right. That's 1.17 kilobytes per second. Divided by 1024, that's 0.0011 megabytes per second. So if we take 3 and we divide it by 0.0011, 3 divided by 0.0011, that is 2,727 seconds. So divided by 60, that's 45 minutes. So the MP3 would take you 45 minutes to download for a 3 megabyte file. Now that's if you were maximizing your modem. That's if you were getting full bandwidth of your modem. All right, so point is things have changed, right? We live in a different world today where our mindset as computer scientists is different. And it really is interesting from a teaching philosophy perspective, because it's easy for me to sit here and say, well, this is how things used to be, and we really need to be careful about memory and stuff like that. The reality is that 95% of the time, or even more, probably 99% of the time, we really don't need to be careful about memory. But we do need to understand the stuff that happened in the past to prepare us for that 1% of the time that we do need to care about memory. Because there are still tasks today that are memory hogs, even by today's standards. Yeah, think about video. So how many of you have TV at home or watch HD content? Maybe you're watching Netflix in 1080p. I think you watch Netflix in 4K. No, 4K, so 1080p. You watch Netflix in 1080p. Okay, so let's think about what that means. So 1080p, that's standard. Well, usually it's called full HD, right? Okay, that's full HD. That resolution is 1920 by 1080. pixels. All right, so 1920 times 1080, 1920 times 1080 is 2 million pixels. Two million pixels. All right, now what's a pixel? Pixel is a little dot of color, right? Well, how many colors do our current TVs, how many colors can they show? So is it just 256 color, or is it a lot more colors than that? Are there a whole bunch of shades of blue, a whole bunch of shades of yellow? All right, so probably 32-bit color, 4-byte color. All right, so let's just operate off of that. So this is number of pixels. Then we're going to have that number times 4. That's the number of bytes for a single screen, single image on your screen. So 8,294,000 bytes. Bytes per image. Now, typically when we're watching TV, if you have a 120, anybody know what kind of hertz their TV has? Anybody have a 120 hertz TV? 60 hertz TV? Everybody in here probably has at least a 60 hertz. So we'll go on the low end because that'll be enough. Okay, so we're going to say 60 hertz. 60 hertz effectively means 60 frames a second. Now you're still at the mercy of who your provider is and how much they're giving you, but let's just operate off of 60 frames per second. That means in every single second, they're showing 60 of these. All right, so times 60. So this is the number of bytes per second for 1080p TV. And we're going to start kicking this down a little bit so we can take that number divided by 1,024, that's kilobytes per second. That's megabytes per second. That's gigabytes per second. So about 0.46 gigabytes every single second. For HDTV. Right? All right, so now you have, how long is a movie? An hour and a half? 90 minutes? You got a 90-minute movie? Or we want to go off a TV show? So we're on Netflix. Let's think about Netflix. So TV shows, an hour-long TV show is like 43 minutes when you have the commercials torn off, right? So this is per second. So we need that times 60 times 43. All right, so 0.463, well, let's do 0.46. 46, so times 60, that's per minute, times 43. That's for a 43-minute TV show. So, over a terabyte. 1,186 gigabytes for a 43-minute TV show. All right, now what kind of speed internet do we have at home? I ask this almost every single class I'm in. You should know it as MSIT students. We're the tech professionals, right? So how many of you have internet at home? All of us have internet at home? Okay. Do you have DSL or you have cable? Cable. Who's your provider? Spectrum? Spectrum? Okay. What speed do you have? You have 64 GB? I promise you that's wrong. All right. So, anybody want to give a more accurate answer? Yeah, download speeds. And when they sell it to you, they kind of lie to you, right? They say, oh, it's going to be 60 meg. But what does that mean? What does 60 meg mean? So do you have like the entry level? So you're probably at 100 megabit now. When you bought it, they probably sold it to you as 60 meg um, cable modem, but now their baseline is 100. So you have 100 meg. But what does meg mean? It's megabit, bit, not byte. It's megabit. But they don't say that. They say meg because it sounds better. Okay? So what is megabit per second? So if you can do, we'll just use your number. We're going to say it's 100 megabit per second. 100 megabit, small b. Okay? Megabit per second. So first we need to do is we need to convert that to bytes. So 100 divided by 8. So that's 12.5 megabytes per second. So now we're in megabytes. All right? So that's how many megabytes we can do per second. If we want to get that into gigabytes, we're going to divide that by 1,024. So 0.012 gigabytes per second. See, look, it even wants to autocorrect it. Okay, this is gigabytes, big B. Okay, that's how many gigabytes per second your internet can do. So that means in 43 minutes, 0.012 times 60, that's in a minute. So 0.72 times 43. So you can do 30.96 gigabytes in 43 minutes. That's how much you can download on your internet. 30.96 gigabytes in 43 minutes. Got it? So that's how much data if you're maxing your connection. Okay, most of the time you're not going to be able to get 100 megabits per second from a single source. When you get, this is called wideband internet, when you get lots of megabits, what it's really for is the fact that you might have 9 or 10 devices in your house that are all using the internet. You have 3 or 4 cell phones, you have, somebody's on a PlayStation, you have 2 Netflix things going, and they're all pulling a portion of that all adds up to that full bandwidth. Make sense? But we'll assume that whatever source so we're going to assume Netflix uses all your data. It doesn't, but we'll assume it does. So you're getting all of your 100 megabits per second. So that means this is the most data you can download in 43 minutes. It's 30.31 gigabytes. All right, now to get a 43-minute show in 1080p is 1,186 gigabytes. So that number minus that number. So you are 1,155 gigabytes short. Now you told me that you watch HD stuff on Netflix. Did you lie? Did he lie? You think he might have lied. You're lucky you didn't lie. Didn't lie. Compression. Okay. So first of all, I'm telling you, in 43 minutes, you are not going to move that much data with Netflix. In fact, you're probably only going to move about a gigabyte of data with Netflix, maybe 2, but way less than 31. All right, so you're not maxing your internet connection. Netflix isn't going to make you. So what I'm saying is what Netflix does is they're taking something that in its raw format is that size. And they are squeezing it down, squeezing it down to something that fits into something smaller than that. By compressing it. Now, what's compression? When I say compression, well, you mentioned it. So what is compression? What does that mean to you? Okay, so we have to have an alternative way of representing the data. All right, so for instance, if this was the internet between us, okay, and I have a 1 terabyte file that I need to send you, and I squeeze it down into, let's call it a 10 gigabyte file, a lot smaller. Okay, I squeeze it way down. Now, I still have 1 terabyte of data here. How do I squeeze 1 terabyte of data to make it feel like it's 10 gigabytes of data? He mentioned you have to have a way of representing that 1 terabyte of data in a different way, such that that 1 terabyte actually becomes 10 gigabytes. I then send you 10 gigabytes, and on your end, you then recalculate the 1 terabyte. You bring it back to what it was. That make sense? Now, the idea is that you have more computing power on your computer than you have bandwidth over the internet. So if we can squeeze it down into something here and then rely on your computer to rebuild it on the other end, things can move faster. That's how compression works. That's why you need a set-top box for your cable TV, whether you're DirecTV, Dish Network, Comcast, Spectrum, whatever kind of TV you have a little box that sits there, right? What's that box? It's a compressor decompressor. Well, really, since it goes one way, it's a decompressor. It receives compressed video signals and decompresses it. That's what it does. It has a special chip in it that knows how to decompress video really, really, really well. Make sense? Because I promise you, you're not getting 300 HD channels all at one time over your coaxial cable. It can't push that much data, so it has to compress the heck out of them in order to get it to your actual television set. Now, what's the problem with compression? Lossless. So we have this idea of something called lossless compression and something called lossy compression. Now, typically, most compression is lossy. Something gets lost in the translation. The idea is that it shouldn't be, we hope it's not noticeable. So if you look at 1080p raw, a raw picture in 1080p versus a decompressed picture that was a compressed 1080p picture, somebody who knows what they're looking for will probably be able to tell you which one was the decompressed one, because they'll see the results of compressing than decompressing. A lot of times you have less shades of black, things like that, because it has to look for patterns. So if 90% of a picture is black, it's going to say, well, let's save ourselves 90% of this by representing all of the black space as something. And then we'll mathematically just create it as black instead of these 13 shades of black that we might have had. That makes sense? All right, so, but we already saw that, at least with his internet, we're not pulling a 1080p show in raw format in 43 minutes. In fact, if you want to do it, what do I need? So I can do gigabytes per second there, 0.012, and I need to move this much divided by 0.012. That's 98,900 seconds. That's minutes. That's hours. All right, so a little bit more than a day. So that's what you do. You sit there, he sits in front of Netflix, says, you know what? Tomorrow, a couple hours later in the evening, I want to watch this show. So I'm going to start buffering now. I'm going to start buffering now. So I can come back tomorrow in 2.5, 3 hours, and my show will be ready. Well, I've moved all that data. That's not how it works, right? You click play on Netflix, and a couple seconds later, it's going. It's cooking. So Netflix must be doing something pretty special with compression, right? That's their magic sauce. Netflix has a very proprietary compression technique for sending data in a high visible quality while highly compressed format. I guarantee if you look at 1080p RAW, it will look better than 1080p decompressed. But to view 1080p RAW takes some pretty ridiculous hardware. To look at live 1080p frames at 60 frames a second, uncompressed, you need quite a bit of processing power to do that. Make sense? Okay, so nobody's really doing that. Nobody's watching just raw video anymore. We can't. Maybe the people who are like editing the movie, you go and see some newest movie in the theaters, they probably recorded it in 4K or something like that. They have some $30,000 computer that they're doing video editing on for the movie. They are working through parts of that movie in raw footage with a $30,000 computer. All local, not sending it over the internet. This is a local file. This isn't something we're streaming anytime soon, but we can fake it with compression. All right, so this just kind of gives us this is something we all deal with every day, right? All of us in here watch Netflix or some sort of streaming stuff. Okay, so the point is that even by today's standards, we have examples of memory usage that is problematic, right? Because right now, nobody wants a 1080p TV anymore. If you go out and buy a new TV today, it'd be a 4K TV, even though there's very little 4K content out there. So fast forward 2, 3, 4 years when there's a lot more 4K content. There's a bunch of 4K stuff on Netflix now, but point is there's not, probably 85% of our content is 1080p. The rest of it is 4K, let's say. But fast forward 2, 3, 4 years when a lot more is 4K, then you go out to Best Buy and you buy a new TV, it'll probably be an 8K TV, right? We're going to... Okay. We just keep jumping ahead even if our eyes can't tell the difference anymore. It is kind of funny when you go back and you, I was at my dad's house this weekend and he, down in their basement where they have like their guest room set up, they have a small TV down there. He has a big TV in like the family room area down there, but in the bedroom they have this small TV. I don't know, it's probably maybe a 17-inch LCD TV. So way better than I had when I was a kid. Okay? And it gets high definition. But it's unwatchable because the TV's too small. And I think back, so when I was a kid, I had a tube TV. I think I had like a 9-inch tube TV, right? And it was in standard definition. You think about today, when you watch TV, like especially sports or something like that, where you can like see their sweat, right? And you just think about how much different the viewing experience is today than it was 30 years ago or 20 years ago. How different it's been. To the point where that's not even watchable anymore. I mean, like if you had to watch like a 15-inch TV, or if you had to watch a 9-inch TV, you would have to be like right up on top of it, right? You couldn't watch that from across the room and it'd be meaningful. It's just things moving, right? It's interesting how our standards change. But in any case, eventually we're going to hit the point where, we're probably no longer going to even use screens on the wall. Just the images will just be put right onto our optic nerves, and they're going to charge you for that. That'll actually be funny. Because right now, like the cable stations or DirecTV, all those places, they charge you like so much for, they give you a box, right, for the TV, but they charge you like $7 a month for the service on that box. And now there's this controversy because if you get one of these new smart TVs that actually has the ability to run DirecTV or something like that without the box, you still have to pay the $7 a month. Because you're not renting the box. The $7 a month is the service to that TV. So if we keep following that model, what will be funny is when we get to the day when they're just doing it right on our optic nerves, they're going to charge us $7 per eye. So they're going to charge us $7 on top of our plan to use our own eyes to view TV. Yeah. That's that kind of thing, right? Oh, you're referencing the one episode where where they record everything. But yeah, just kind of fascinating stuff. But the punchline of all this for us, from a computer science perspective, well, two punchlines. First of all, you need to know what kind of technology you have at home. As IT professionals, and I mean, if you walk into a job interview for an IT job, and they ask you what kind of internet speed you have at home, that should be an easy question. And if you are making up numbers like you did, they're going to kick you out. You need to know. You're the technology experts, right? I mean, that's an accurate statement, isn't it? I mean, it's one thing if my mom doesn't know what kind of internet speed she has. In actuality, she does, because I make sure she does. But my mom's not a computer science person. But it would be okay for her to not know what her internet speed is. But for a person with a master's degree in IT, you should know what your internet speed is. You should know about all the technology you have in your house. You should know about the what kind of wireless router you have, all this stuff. You need to know about that stuff because that's part of the competencies that you're trying to tell an employer you have. Does that make sense? And kind of an interesting side note from that is I asked that question. How many of you have been in a class with me before I've asked that same question? I ask it in almost every class I teach. The answers I got in here are not dissimilar to the answers I usually get. Usually there's maybe one person in an entire class who knows what the speed of their internet connection is at home. And that's ridiculous for a technology expert. So do better. Know what kind of stuff. Do you know what the specs of your laptop are? No. It's a Dell, first of all. Do you know what the specs of your laptop are? Oh, okay. Hit me with it.
i5, dual-core processor, 1 is 2.6 and 1 is 1.9.
Okay.
8 GB RAM, 1 TB hard disk.
Okay. Is it a solid state or a mechanical hard drive? I already know the answer, but let's see if you get it right.
I think it should be solid.
You think it should be solid state? What's the size screen on that? How big is the screen? A 13-inch max? Probably less than that. So it looks like a tablet kind of. Is that a Surface Book? Yeah. It's and you have a 1 terabyte drive in it? You're positive it's a 1 terabyte drive?
Oh, not this one.
Oh, your other laptop. Okay. If it has a 1 terabyte drive in it, it's not solid state, unless you paid a lot of money for it. Did you pay more than $3,500 for it? No. What's common in laptops today is if you might have 2 drives in it. Sometimes you'll have a laptop that comes with a 1 terabyte standard HDD, standard hard drive, and then it might have a 128 or a 256 solid state SSD. Because the solid state drives are the fast ones. You want to have your operating system on there and stuff like that. You put all your downloads into that 1 terabyte drive. Because 1 terabyte, a normal hard drive, it doesn't cost much. Call it $90. A 1 terabyte solid state drive, way more than $90. They're expensive. Okay, but that was pretty good. Yeah, I didn't get you to the very end there. Okay, you don't know what you have, right? No, Intel or AMD? Intel. It's like you got one. Got. Okay. All right, do you know what's in your computer? She was looking it up. It's coming to me next.
But yeah, it's in Lenovo X1 Carbon. It's an Intel. It's about 8 gigabytes of RAM.
You know if it's an i7, i5, i3?
It's an
i7,
i7.
okay.
But I just don't know. I don't think it's a solid state.
It's a pretty new computer, right?
It's a generation 2, so I think that's like 2 years back.
Oh, it's a second generation i7? Oh, that's an old i7. Are you sure it's second generation i7?
Yeah.
because we're on 7th generation i7 right now.
No, I'm talking about the carbon generation.
Oh, I gotcha. If it's a 2-year-old machine, it's probably either an i7 6500 or 5500. Might be a Series 5 i7, which, I mean, it's fine. i7s are good.
Right.
You know, the newer ones are faster, but only in very specific tasks. You know, when they say this year's i7 is 30%, up to 30% faster than last year's, that's performing a very specific task that they've added to the chip. Most tasks are going to be pretty equivalent to the previous model. All right, well, that's not bad. You know what you have at home?
I have an 8th generation Intel i7 processor.
Oh, she's got the newest one. This is a new machine, right?
I bought it recently.
Because those just came out. Okay. Is this a laptop or a desktop? Laptop? Okay. All right, keep going. What else can you tell me?
I don't remember.
Screen size?
I think it's 30. I don't know.
Not a laptop. How big is the screen? Is it bigger than this?
Yeah, it's
A little bit bigger, like this? So it's probably a 15-inch screen. It might be 17. It's either 15 or 17, not 32. Not a laptop anymore. If it's 32, it's not a laptop. Okay, what's the company? Oh, Lenovo? Okay. Yeah, so I don't know if they make a 17, so it's probably 15.6. Let me guess, probably 16 gigs of RAM. It might be even 32, probably 16. You think you have 32 gigs of RAM? How much did you spend on it?
It was a gift.
Good gift. That's a good gift. Okay, so in any case,
Is it easier to replace in your computers?
is it easier to replace?
Like to put a higher size?
It's all a cost thing. So a solid state drive versus a standard hard drive. On laptops, they pretty much look the same. Well, actually, that's not even a true statement anymore because the solid state drives can be physically a lot smaller. In the early days of solid state drives, they actually look the same because they would have the same form factor when you put it in.
Right, and I'm asking that because during my internship, one of our tasks was to actually upgrade the computers and put
Yeah.
higher size solid states in them. So I'm just wondering if they're not built into the machines, so you get what you get.
Unless it's Apple, most of them do not build it into the machine. And what I mean by that is soldering it. So like this machine, I can't upgrade the hard drive in this because the hard drive is soldered to the board, which they claim will be faster and probably is, but then it's not maintainable, right? But for most machines, when you pop it open, a solid state drive versus a mechanical drive use the exact same serial ATA connector. So you yank it off the old hard drive, you put it onto the new hard drive, and then you just need, because typically today solid state drives are smaller, you have to have a way of just kind of keeping it in there so it's not flopping around. So like I put a solid state drive in one of our desktop workstations, and you know the normal hard drive is like that, right? Well, the solid state drive is like this and like that thin. Fitting into the same slot, you kind of have to find a way to keep it in there so it doesn't bounce around and stuff like that. So it's that's the bigger issue. But typically, if you're looking for capacity, anything much bigger than 256 gigabytes in solid state is going to start getting a little pricey. 512 has dropped into the range of affordable, but a terabyte solid state drive is still pretty costly. So I think we'll just look. So if we do 1 terabyte normal drive, it's going to be under $100. Yeah, here. 1 terabyte. So this is a pretty high performance. This is a 7,200 RPM standard hard drive. All right. So this is $50. So if we do 1 terabyte SSD, that number is going to go up. so here's that's $450.
This is what we use for servers.
Not necessarily. I mean, to be honest, if you want performance out of your computers, the first thing, so we're going way off script here, but this seems like you guys don't know anything about your technology, so I guess we'll go with this. The The first thing you should upgrade in your computer is your hard drive. The hard drive. You need to have enough memory to do the stuff you're going to be doing, but what thing you'll feel the most is the hard drive. So for instance, if you got the latest, greatest Intel processor with enough memory, 16 gigs of RAM, whatever, blah, 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 and you had that other hard drive, the 1 terabyte normal hard drive in it, it will feel slow to you because of that hard drive. That hard drive is orders of magnitude slower than a solid state drive. It's not like twice as slow. It's hundreds of times slower.
I use Android in the Android Studio. It's fast in the tab, slow in my computer.
Yep. And is it a desktop computer or a laptop? Okay. If it's, do you download a whole bunch of stuff on that computer? Or not very much? Like, could you get by with 256 gigs of hard drive space? Pretty easily? Heck, I would just do this. Who makes the laptop?
HP.
Oh, it's HP? Okay, so chances are you might be able to do an M2 one. You'd have to look to see if your HP supports it. But worst case, you could, because then you could keep your other hard drive in there because it might have an M2 spot where you could just plug it in and have a second hard drive. Otherwise, you could yank your current hard drive and for $85 have a Samsung Evo 250 solid state, and that computer will feel way faster. Night and day. Not even close. That's the first thing you upgrade in your computer is your hard drive speed. Now, one solid state to another solid state, just because something has a little bit more read-write, you're not necessarily going to feel that. Because now you're talking about, fractions. But the difference between a mechanical hard drive and a solid state drive, night and day. Not even close. Yeah, so if we do, what's it? I think it's M2, right? Yeah, so here's a 256 M2. So if your machine supports M2, your laptop, if it has an M2 port on it, which a lot of the newer laptops do have that, so it's entirely possible you do. For $90, you don't even have to take your current hard drive out. You just put this one in with it as an M2 port. It's inside the computer. It wouldn't be a side slot. This guy, got to get him A+ certified or something. Okay, it'll be inside the computer. But if it has an M2 port, then you can have two hard drives. The one that your 1 terabyte one that's already in there, but put your operating system on the solid state. And then any application that put all your like Android Studio, that stuff, put it on the solid state. It'll feel like a brand new computer for $80. Done. See, the more you know. I wonder why that is. Maybe you can enlighten me. Why is it that? Because this isn't just like I'm saying. We're picking on him. Well, I'm really picking on most of you, but mostly him. But he's not like the exception. This is the kind of the norm. Why is it that folks coming through a master's program in IT know so little about modern technology? Where's that being lost? Where is it being missed?
I think in our earlier classes, so here, I know we have the systems, not the systems development class. We have a class where we learn just about your operating system, troubleshooting,
Okay.
just this basic stuff. But I never had that in my undergrad. A lot of things I know about my operating system I learned it from this master's class. And when we actually started that class, it was started with the expectation that you would have learned that in undergrad.
I see.
But that wasn't the course offered in undergrad.
Mm.
And it's the same for a lot of my other friends that I know that have taken CS courses undergrad in other schools as well.
Okay. Yeah, interesting. I mean, because really, you could cover the stuff I mean, just think about what we've talked about just today in an hour. I mean, we've talked about quite a bit of stuff. So, I mean, you could take a week of a class and pretty much, I mean, it's not like this stuff is hard to understand. It's just you've never been exposed to it, right? So take a week of a class maybe and just bring you up to speed. Yeah, I don't know, just very interesting that.
And really, after you learn it the first time, you just always be curious. Like, if you're a curious person, you always want to
Yeah.
know.
And I wonder, how many of you have built your own computer before? Yeah, please tell me you haven't. Because if you built your own computer, and all right, so and maybe that's it. I wonder if because laptops have become so commonplace now. Most of us have laptops as our main computer, right? And people don't really build laptops. People build gaming desktops. You know, build your own desktop computer. But a lot of us don't even, how many of you even have a desktop at home?
I do. I have one that was built by my coworker.
Okay.
And just replaced the 2 parts, which is upgraded with the
Yeah.
processor.
But in general, you rely on your laptop a majority of the time, right? So the fact that you have a desktop, you could live without it. And I think that's becoming more the norm. And maybe for technology students, the fact that you aren't forced to, well, I mean, not even a forced thing. Like as a technology fan, if your main computer was a desktop, you would save money by building your own desktop versus buying a desktop computer. So most of you would have gone through that experience of picking out the individual parts, putting them all together, doing that. But now that technology's moved towards mobile, I mean, we don't build our own cell phones. We don't build our own laptops. So maybe it's kind of like a lost art or something like that, where the only people who really know about that stuff is like the folks who are building their gaming rigs, computers for doing PC gaming. Just very, very interesting to me that, you know, that the amount of information that people, our modern students aren't aware of. And I'm always fascinated to find out why. Because, I mean, it's not a stupidity thing. I mean, we've talked about all this stuff, and even he understood it as we talked about it, right? Yeah, I mean, it's just you were never exposed to it, right? It's not hard to understand. You just never heard about it, this stuff before. So, yeah, that's a very fascinating thing to me, where that stuff gets lost. All right, so, again, twisting back here then, at the very least, we can appreciate that problems today do exist where memory can still be a problem, right? So we do need to understand, we do need to have an appreciation for being good stewards of the amount of memory we do have, so that in a situation where we do need to be careful about it, especially in the IT industry. You know, what's big in the IT industry today? If you guys are working at a university or an enterprise somewhere, I mean, yeah, you're probably not. I mean, there's plenty of jobs in the cable industry where you would be handling stuff like this, compression and that kind of stuff. But even if we just look at, like, if you were working in IT here at Concordia, what are the types of problems that you're dealing with here? You're going to be dealing with kind of probably video conferencing type stuff, which isn't quite broadcast television, because you're not trying to take, here's a signal and get it out to, 10,000 users. Instead, we got 2 people that need to talk to each other, and we want them to have a good, clear conversation that's, crisp. If that's the case, that would be the tools because you're going to be working with existing tools, video conferencing tools, but then you're going to have to be thinking about, well, what kind of bandwidth do these things need in order to perform at their best, and then do some quality of service type stuff, QoS type stuff, to ensure that during the time period of that video conference, you are getting the bandwidth necessary for accomplishing that. And that, somebody over in dorm XYZ isn't downloading, 100 gigabytes of video during the same time and yanking all your bandwidth away. So we need to do, throttling on that. So slow them down so we have enough active bandwidth for the video conferencing. Those are the kinds of problems that an IT person would be dealing with, because you're performing a magic trick, right? If we're talking to somebody across the pond over at, the small pond, over at, Ann Arbor, and we're having a video conferencing thing with them over the internet, we're reliant on that being secure. I mean, probably most video conferencing things don't need to be secure, but sometimes they do. I mean, I'm sure, the president has lots of video conferencing stuff on a daily basis, and that probably needs to be secure, right? Okay, so you got to secure it. The quality needs to be there. We can't have him talking to Putin or something and have it be a bad connection. Who knows? But the punchline is that these are the kinds of problems that IT professionals are going to deal with, and memory is still at the forefront. The amount of data we're working with. So, you can think of memory in terms of RAM. You can think of memory in terms of hard drive space. You can think of memory in terms of, the pipe that the internet data is flowing over. Okay, so memory is a measurement of bits, right? Regardless of how we're storing it. Are you storing it on a mechanical hard drive, on a solid state drive, in RAM, random access memory, which is volatile memory. So your power, if you lose power on your memory, it's gone. Then you have to restart your computer and load the stuff back into RAM. So regardless of where you're storing those bits, that's memory. Bits are memory. Make sense? And we need to be able to deal with that stuff. All right, so we need to look at ways that we can handle this stuff from a computer programming perspective. We've covered this already where, I recognize that most of you are not going to leave this course and go out and become full-time developers. Some of you will. I mean, we've had people come out of MSIT and go and become full-time programmers and never do normal IT stuff. They do programming stuff. But I recognize, kind of reading the temperature of the room, I think most of you are going to go out and be IT professionals, right? You might be the slight exception. Okay? You're pretty good at programming. But I don't think that you don't want to be a programmer, right? Yeah. But she's actually pretty good. You should talk. I haven't picked on you yet. I'll get over there. All right. So, but in any case, having this knowledge and understanding what's happening under the hood is at least going to tell you about what's happening in the hardware you're working with. When you're working with a router, routers have algorithms and how do they route information from, this point to this point to this point to this point, and those routing algorithms, one of them is an algorithm called RIP, and those routing algorithms are based on these kind of data structures. That kind of makes sense? Because they're going to have a finite amount of memory on them to begin with, and they have to be able to roll with the punches. A router doesn't know whether it's going to have, 1 gigabyte of data moving through it at a given second, or 1,000 gigabytes of data moving through it at a given second. And it needs to be able to roll with those punches. So the underlying algorithms that they're using they're important things for us to understand, whether you're the one writing the algorithm or you're the one using that router and having to understand or debug a problem that it's running into when you see a certain behavior and it's just not acting the way you want it to act, being able to deal with that. Does that make sense? All right, so let me just quickly introduce the next thing we're going to talk about, and then we'll take a break, and then we'll come back and talk about that, and then we'll head over to our Grace thing. So I kind of started today talking about this idea of linear linked data structures. And we've talked about these linear ones. And they're good. When you need to store lists of stuff, they're good. But now we want to start talking about nonlinear linked data structures. And the first one we're going to look at is something called a binary tree. Okay, sometimes a binary tree is a pretty generic name for it. Typically, we're going to think about these as binary search trees, BSTs. But after break, we'll come back and we'll talk about these specifically. How many of you have heard of binary trees before? In passing at some point, or you've heard of a tree data structure? We've all experienced it before. When you look at your directory structure is stored in a tree format, right? So directories is effectively a tree. You have a top level that holds a whole bunch of subfolders. Each of those folders can hold subfolders, so it's a directory tree. Make sense? Binary trees specifically, so a directory tree would be something called an n-ary tree. It's a fairly generic type thing. Binary trees are used for searching, organizing data in a certain way. That's what we'll talk about after break. So it's more of a performance type thing. But in any case, questions about any of the stuff we've talked about up to this point? Has everybody been appropriately humbled to some level? Especially you? I love this guy. I really do like you, actually. I've had him in several classes. I do like him. All right. So let's take, let me actually do the math. So because I want to be done at 7:45. So let's take 15 minutes. Come back at 6:30, finish at 7:30, then we'll have a break. Okay, yeah. So 15 minutes, we'll come back at 6:30 and